This small workshop sits tucked between banana plantations in rural Karnataka, India. And from the outside, it looks like any other metal-roofed structure with faded paint and a hand-painted sign. But step inside, and you'll see something most people throw away, being transformed into something restaurants and food vendors actually pay for. Every single day, this place turns banana peels into food-safe packaging using machines you could probably build in your own garage. No high-tech robotics, no million-dollar presses, no computer-controlled systems. Just simple mechanical advantage and a process that's been refined over thousands of trial batches. The air smells faintly sweet, like overripe fruit mixed with wet paper, and the floor is spotless, despite handling what most consider garbage. Workers move with practiced efficiency, each knowing exactly when the next batch needs attention. You're about to see how a fruit peel becomes a plate strong enough to hold curry, and why this process rejects more material than most factories would ever dare. The journey starts 15 kilometers away at the wholesale fruit markets in Bangalore, where vendors peel bananas by the ton for juice stands, smoothie shops, and processing plants. Those peels used to go straight into landfill trucks, contributing to the city's 1,200 tons of organic waste per day. But now they're collected in large plastic bins and transported to the workshop within 6 hours of peeling. Timing matters here because banana peels oxidize fast, turning brown and losing structural integrity as enzymes break down the cell walls. The workshop receives about 200 kilograms of peels every morning, delivered in a small pickup truck that makes 3 runs a day from different market zones. The driver knows to keep the bins covered with wet burlap during transport to slow oxidation and prevent fruit flies from contaminating the load. When the truck arrives, workers wearing gloves and aprons immediately sort through the pile, rejecting any peels contaminated with plastic, metal, excessive dirt, or peels that show signs of rot or mold. You'd think this step would be quick, but they reject nearly 20% of what arrives because one piece of contamination can ruin an entire batch of packaging. A single staple from a cardboard box, a piece of plastic wrap, or a moldy peel can create weak points or contamination that shows up days later when a customer is using the tray. The accepted peels go straight into a large concrete washing tank, filled with clean water and a small amount of natural detergent made from soap nuts grown in the same region. This isn't a gentle rinse. Workers use long wooden paddles to agitate the peels for a full 10 minutes, making sure every trace of dirt, pesticide residue, and fruit sugars gets washed away. The water turns murky brown almost immediately, and you can see bits of stem, tiny insects, and the occasional piece of fruit flesh floating to the surface. The sugars are actually a problem because if they remain in the pulp, they'll attract bacteria and insects during drying, which can spoil entire batches. After the first wash, the peels are transferred to a second tank with fresh water for a final rinse, and workers manually squeeze each handful to force water through the peel's natural pores. The entire washing process uses about 300 liters of water per batch, but here's the interesting part. That dirty water doesn't go to waste. It's filtered through a simple sand and gravel system, treated with beneficial bacteria that break down organic compounds, and then used to irrigate the banana plants that will eventually provide more peels. The workshop has a small holding pond where this recycled water sits for 48 hours before irrigation, giving the bacteria time to work. Nothing leaves this workshop without being used twice, and the water recycling system alone saves about 70,000 liters per month. Now comes the transformation. The clean peels are fed into a machine that looks like an oversized meat grinder, but instead of blades, it has rotating drums covered in small metal teeth arranged in a specific pattern. This is the pulper, and it's the heart of the old-school process. The machine was actually built by a local metal worker based on designs the workshop owner sketched after studying paper pulping equipment in old engineering textbooks. As the peels get forced through the drums, the cellulose fibers inside start separating from the softer tissue, and the natural pectin that holds the peel together begins to break down. It's loud, wet, and smells intensely of banana, but what comes out the other end looks nothing like a peel anymore. It's a thick fibrous pulp that resembles wet cardboard mulch, and if you look closely, you can see individual fiber strands about 2 to 5 millimeters long. The machine runs continuously for about 30 minutes per batch, and workers have to wear ear protection even though it's just mechanical grinding with no motors louder than a kitchen blender. The drums rotate at exactly 45 revolutions per minute, a speed determined through trial and error. Too fast and the fibers shred into powder that won't bind properly. Too slow, and you get chunks that create weak spots in the final tray. One batch of 200 kilograms of peels produces roughly 60 kilograms of usable pulp. That means you need about 3 peels to make one single-use food tray. And when you consider that most people throw away at least 1 banana peel per week, the scale of available material becomes clear. The pulp drops into a large mixing vat where the real science happens, even though it looks primitive. Workers add specific amounts of water to bring the consistency to what they call porridge stage, where the pulp flows but still holds its fiber structure. They also add a small percentage of natural binding agents, usually tapioca starch or cornstarch, which helps the fibers lock together during molding. The ratio is critical. Too much water and the trays will warp during drying. Too little, and they'll crack under pressure. The workshop has tested hundreds of ratios over the years, and they've settled on 65% pulp, 30% water, and 5% binder by weight. A worker checks the consistency by hand, literally squeezing a handful to see if it drips or clumps. If it holds together but releases water when squeezed hard, it's ready. If not, they adjust and mix for another 5 minutes using a simple paddle mixer powered by a small electric motor. The mixing process also introduces air bubbles into the pulp, which will create tiny pockets that make the final tray lighter without sacrificing strength. Temperature matters too. The vat is kept at around 25 degrees Celsius because warmer temperatures cause the starch to activate too early, and colder temperatures make the mixture too stiff to work with. The mixing vat feeds into a series of simple molds made from perforated aluminum sheets shaped like trays, bowls, and rectangular containers. Each mold sits on a wooden frame, and here's where the old-school approach really shows. There's no automatic press, no hydraulic system cycling every few seconds. Instead, workers manually ladle the pulp mixture into each mold, spreading it evenly with wooden spatulas to ensure uniform thickness. They're aiming for about 4 millimeters of compressed pulp, which will shrink to roughly 3 millimeters after drying. The molds have drainage holes spaced exactly 8 millimeters apart, a measurement that allows water to escape without letting fiber strands pull through. Once filled, the molds are stacked onto a simple lever press, the kind you might see in a small print shop from the 1950s. A worker pulls down on a long metal arm, and the leverage forces a flat metal plate down onto the stack of molds, squeezing out excess water through the perforations. The water drains into a collection tray below and gets pumped back into the mixing vat. One press cycle takes about 15 seconds of sustained pressure, and you can hear the water hissing out as the pulp compresses. The worker has to apply consistent force because uneven pressure creates thick and thin spots that will show up as weak points later. Each worker presses about 40 molds per hour, and they rotate shifts every 2 hours because the repetitive motion can strain shoulders and backs. After pressing, each mold is carefully separated and moved to the drying area, which is essentially a large open courtyard with metal racks positioned to catch maximum sunlight. This is the step where most batches either succeed or fail, and it's also the step that takes the longest. Banana fiber has a high moisture content even after pressing, somewhere around 45%, And if it dries too fast, the trays will crack as the outer surface shrinks faster than the inner core. Too slow, and mold spores will colonize the surface within 8 hours, especially during humid monsoon months when relative humidity can hit 90%. The workshop has learned to dry trays over a 2-day period, rotating them every 4 hours to ensure even air exposure on both sides. Workers literally walk through the racks with clipboards, marking which trays have been rotated and checking for any signs of warping, cracking, or mold. During monsoon season, when sunlight is scarce, they use a simple wood-fired drying room where trays sit on racks above a low controlled fire fueled by scrap wood and dried banana leaves. The temperature never exceeds 50 degrees Celsius because higher heat causes the starches to caramelize and the trays to become brittle. Workers constantly monitor for white spots, which indicate mold, and any tray showing contamination gets pulled immediately and sent back to the pulping stage. The drying room has a chimney system that creates natural convection, pulling hot air up and across the trays without needing fans or blowers. This passive airflow is critical because forced air can create uneven drying patterns. Once dry, the trays are hard, lightweight, and surprisingly rigid, but they're not food safe yet. The surface is rough and porous, which means liquids could seep through and bacteria could colonize the tiny crevices between fiber strands. To solve this, the workshop applies a thin coating of food-grade beeswax mixed with a small amount of plant-based resin extracted from pine trees. This isn't sprayed on with fancy equipment or dipped in automated baths. Workers heat the wax mixture in a double boiler until it's liquid, maintaining a temperature of about 80 degrees Celsius. Then use natural bristle brushes to paint a thin layer onto both sides of each tray. The technique matters here. Brushing in long, even strokes ensures the wax penetrates into the pores without pooling on the surface. Too much wax and the tray becomes greasy and unpleasant to handle. Too little, and moisture can still penetrate. The wax fills the pores, creates a moisture barrier, and gives the tray a slight sheen that customers associate with quality. It also makes the trays smell faintly of honey, which is a selling point for restaurants trying to offer eco-friendly dining experiences. The wax coating adds about 2 grams to each tray's weight, but it increases water resistance by over 300% based on tests the workshop has run. The beeswax is sourced from local beekeepers who maintain hives near the banana plantations, creating another closed-loop system where the workshop supports local agriculture. After coating, the trays go through a second drying phase, this time just 4 hours in ambient air to let the wax fully cure and harden. Then comes finishing. Workers use simple grinding wheels to smooth any rough edges, ensuring there are no splinters or sharp points that could cut a customer's hand. They also check for warping by placing each tray on a flat reference surface made from a sheet of glass. Any tray that rocks or doesn't sit level gets rejected. The rejection rate at this stage is about 8%, which might seem high, but it's essential for maintaining the workshop's reputation. Rejected trays don't go to waste. They're broken up and sent back to the pulping stage to be remade. The grinding process also creates a fine dust made of dried banana fiber and wax particles, so workers wear dust masks, and the area is swept clean twice per shift. Now it's time to prove these trays can actually do the job, and this is where you see if days of work will pay off or end up back in the pulper. The workshop runs 5 tests on every batch, and each one simulates real-world conditions that restaurants and food vendors will subject these trays to. First is the weight test. Each tray is loaded with 5 kilograms of wet sand, which simulates a heavy meal with gravy or sauce. The tray has to hold this weight for 10 minutes without cracking, bending more than 5 millimeters, or showing any sign of structural failure. Workers place the loaded trays on a rack and literally set a timer. If a tray fails, the entire batch gets flagged for review because it indicates a problem with the pulp ratio, pressing pressure, or drying time. Second is the water resistance test. A tray is filled with room temperature water and left to sit for 30 minutes. After that time, the bottom surface is checked for any moisture seepage using a simple paper towel test. The towel is pressed against the bottom, and if it comes away wet, the tray fails. A few drops are acceptable, but if water is actively dripping through, the batch fails. The beeswax coating is critical here, and this test has led to dozens of formula adjustments over the years. Third is the heat test. Trays are placed in a simple oven at 70 degrees Celsius for 20 minutes, then removed and checked for warping, cracking, or delamination, where the fiber layers separate. This simulates a hot meal sitting in the tray during transport or under warming lights at a buffet. The trays also can't release any odors when heated because customers won't accept packaging that makes their food smell like banana. Fourth is the drop test. Trays are loaded with 2 kilograms of weight and dropped from a height of 1 meter onto a concrete floor. They have to survive without cracking or losing structural integrity. This simulates the rough handling that happens during transport and service. Fifth is the oil resistance test. A small amount of vegetable oil is poured onto the tray and left to sit for 15 minutes. The oil shouldn't penetrate the wax coating or cause the surface to break down. This test was added after early batches failed when customers used the trays for fried foods. About 92% of batches pass all 5 tests on the first attempt, and the 8% that fail usually have issues traceable to humidity during drying or inconsistent wax application. Approved trays are stacked in groups of 50, wrapped in recycled paper, and labeled with a simple stamp showing the production date and batch number. There is no fancy packaging, no plastic shrink wrap, just paper and twine. The labeling is important because it allows traceability. If a customer reports a problem, the workshop can trace it back to the specific batch and review every step of that production run to identify where the issue occurred. The workshop produces about 3,000 trays per week, and they're sold to local restaurants, catering companies, and food trucks within a 100-kilometer radius. Delivery happens twice per week using the same pickup truck that brings the banana peels, creating an efficient loop where the truck is never empty. Price-wise, these trays cost about 30% more than plastic alternatives, but they break down completely in soil within 45 days compared to plastic's 400 years. The workshop has documentation showing that buried trays start fragmenting within 2 weeks and are completely gone within 7 weeks. Customers aren't just buying packaging, they're buying a story they can tell their diners, and many restaurants display these trays prominently as part of their sustainability messaging. The workshop employs 12 people full-time, most of whom have been here since the process was developed 6 years ago. They wear gloves, aprons, and hairnets despite working with what started as garbage, because the final product has to meet the same hygiene standards as any food contact surface. The workshop is inspected quarterly by local health authorities, and they've never failed an audit. Every surface gets sanitized at the end of each shift using a simple chlorine solution, and the pulping and molding areas are kept separate from the drying and finishing areas to prevent cross-contamination. Workers go through hygiene training every 6 months, and there's a strict policy about hand washing before touching dried trays. The workshop also maintains temperature and humidity logs for the drying areas, creating a paper trail that can be reviewed if quality issues arise. One of the most interesting aspects of this operation is how it handles scale limitations. The workshop could theoretically increase production by adding more molds and drying racks, but they've chosen not to. The owner explains that maintaining quality at this scale is manageable, but doubling production would require automation they can't afford and don't want to introduce. The entire philosophy here is that simple machines operated by skilled workers produce better results than complex machines operated by button pushers. Every worker can identify problems by sight, sound, and feel, something that would require expensive sensors in an automated system. When the pulper starts making a different sound, workers know the drums need cleaning. When the drying trays feel too heavy, they know humidity is affecting the process. This knowledge comes from repetition and attention, not from computer readouts. The economics are interesting too. The workshop pays market vendors a small fee for the banana peels, about 10 rupees per kilogram, which is far less than landfill disposal costs, but enough to incentivize collection. The raw material cost for one tray works out to about 2 rupees. The beeswax adds another 3 rupees, and labor and overhead bring the total production cost to around 8 rupees per tray. They sell each tray for 12 rupees, creating a profit margin that allows the workshop to operate sustainably without outside investment. Compare that to plastic trays that cost about 9 rupees each, but create environmental costs that never appear on any balance sheet. The workshop has calculated that they've kept approximately 50 tons of banana peels out of landfills over the past year, which translates to reduced methane emissions and less pressure on waste management systems. What started as 200 kilograms of discarded banana peels is now 1,500 food-safe trays ready to hold someone's lunch. The waste product from breakfast fruit just became the container for dinner, and it happened in a space smaller than most people's garages using machines that don't need a computer to run. Workers are already preparing the next batch, cleaning molds and checking wax levels for tomorrow's production. The cycle continues 6 days a week, turning garbage into value one pressing at a time. This is what old-school manufacturing looks like when it's done right. Simple, repeatable, and profitable without a single ounce of plastic. The workshop proves that you don't need high-tech solutions to solve modern problems. You just need people willing to pay attention to details that others ignore. Every tray carries the fingerprints of the workers who made it, and that's something no factory robot can replicate.